So good morning, all of you. Am I audible and the screen is visible?
Yes, sir, you are audible.
Okay. So today is the day when we start, I would say BPSK. Okay. So BPSK, QPSK, and I would try doing QAM. Maybe on Friday. That is on Friday we have our last lecture. But after that, if at all one or two lectures more are required, then I will record them and put it on the drive so that you all can view it before the exam at least. Okay, and this way we will complete our course with the study of the basic modulation schemes. So last lecture we did the remaining parts of the ML detector, or you can say ML decoder, and we found out that why the Euclidean distance is the way to decode most of the, you can say, modulation schemes or whatever we have been doing in the lab. We were using the minimum distance decoder. That is basically an ML decoder, and it is an optimal decoder if your messages are equal probable. Okay, so we found out that. Then we came to the concept of passband transmission. Now, passband transmission simply says that you have to transmit in some band, or you already have a signal which is in a particular band, which is of this form. That is, it lies from F1 to F2 with some FC, which is in between F1 and F2, such that this FC is quite far away from the D, that is F equal to 0 point, and this F1 and F2 are nearby this FC. So that is the way we defined our passband signal. So it may be the case that the signal itself is passband, or you have a baseband waveform, which due to the constraints of the band at the baseband being unavailable, you have to just translate it to a different band and transmit. So mostly that would be the case, that all the information which you have at the source mostly would be baseband. So you need to up convert it, or you need to translate it to a different band. This can be easily done via the sinusoidal functions, that is sine of omega ct or cos of omega ct. Why? Because they are Fourier transform. They implicitly are passband because they have the spectrum which is away from 0, centered at omega c and minus omega c, and that to delta functions. Okay. So if at all you convolve your frequency spectrum with their frequency spectrum, you will get that your spectrum gets shifted to omega c and minus omega c. This is the underlying principle for AM as well. Okay, amplitude modulation. So I think you must have done it there in the course analog communication. So that is the main logic that generally we do this. Now, because of this, what happens is that mostly we would be having the transmitted waveforms as some variation of these cosine and sine waveforms. Okay, because ultimately now they will dominate the whole process. This xt is although important, this is the baseband signal, but now this baseband signal, what needs to do is that it can either change its amplitude, the amplitude of cosine waveform, it can change the phase, or it can change the frequency. That is what we saw. Okay, because this is now the primary waveform which is going, that is a cos or sine. Because this is a high frequency waveform, this xt would be a low frequency signal. Why? Because xt spectrum is around the baseband, it contains frequencies which are near to 0. Okay, it means its variation is very, you can say, smooth as compared to the variation of cos, because cos will have rapid transitions because of a higher value of omega c as compared to the bandwidth of the baseband signal. So mostly this would dominate this. Okay, well, the changes in the signal will be because of the cos and sine. So those changes you can just you can control, or you can modulate that with the help of either changing the amplitude, omega c, or phi. So we found out that in the case of analog modulation, these three things were called as AM, FM, and PM, that is phase modulation. And in the case of digital modulation, now why digital modulation? We saw that because the message points, or the possible messages which you can transmit or which you will be transmitting are finite. Okay, because of the process of sampling, because of the process of quantization, it means you have converted your continuous valued information to discrete valued information, and that discrete valued information belongs to a finite set. ठीक है, मतलब आप ये नहीं कह सकते कि इंटीजर्स हैं, इंटीजर्स भी डिस्क्रीट हैं, बट अगर इफ यू से दैट complete set of integers, then it's like an infinite possibilities. Okay, because minus infinity to infinity you will have infinite integer values starting from, let us say, minus some 10 raised to power 9 to 10 raised to power 9. So that is not basically digital modulation. Digital modulation says that the values are discrete, but they belong to a finite set as well. Maybe that is minus 5 to plus 5, integers from minus 5 to plus 5. So with that as the case, you will have finite possibilities. So with finite possibilities, you will come up with the concept of shift keying. I think I explained it in the last class that why we call it as a shift, first of all, because you will have discrete shifts if at all there is an amplitude. Same will happen with frequency, and the same will happen with phase. And keying means that there is a sequence of information that will decide what is the shifting of the sine or cosine waveform. Okay, so we saw that this ASK, FSK, and PSK, the three forms which arise. ASK we won't be mostly studying. Why? Because ASK has quite a parallel with PAM. Okay, pulse amplitude modulation. Although we didn't cover, you can say M-ARI PAM. हम लोगों ने अपने कोर्स में M-ARI PAM study नहीं किया. Mostly we studied only binary PAM. And M-ARI PAM is important if at all you are very interested. If you are going through the textbooks, you can read it from there. Not very important right now because our focus will be mostly on BPSK and QPSK. The reason being that, okay, then I will just, when we start the lecture, I will write it down there. So we said that this is the passband transmission model. I think this is a repetition of the detection theory, whatever we studied, I think 2 lectures before. So I am not repeating that. I am starting with the lecture today. It's quite simple. Okay. So one thing which I need to write about ASK and PSK is, let me just write. Yes, one thing is that as compared to ASK, both FSK and PSK, both PSK and FSK signals have a constant envelope. How? You can see that if suppose this was your carrier signal, so if you are either changing this phase with discrete points or you are changing this omega, see this is fixed. Okay, this doesn't change. So you can say the envelope is constant. Now if this A is a constant number, so the envelope is like this. This is the envelope. And the signal is varying in between this. Now in the case of FSK, suppose this is the frequency. Now if suppose that then there is a change, the frequency will increase. Okay. A typical example of FSK. If at all you need to see this, let us go back and see the textbook. It gives a very nice picture. So this is what is the cases. So the A is amplitude shift keying. It says that if 0 is represented by a level 0, so there is no waveform here, and 1 is represented by the waveform, so you will have the waveform whenever one comes. And this waveform has a constant amplitude right now, this particular, when 1 comes. But now you can see that throughout the time, this waveform doesn't maintain the same amplitude. Here it is 0, then it takes some value, then 0, then takes some value. But what is happening with the case of PSK and FSK? This is PSK. Okay, phase of the waveform shift, and this is FSK. So you can see that when it is 0, so it has a particular frequency. Once the 0 goes and 1 comes, the frequency increases. Again, when the 0 comes, the frequency comes back to what the initial value was, or whatever you have chosen for the 0. And when 1 comes, it again, the frequency increases and it goes. Now the envelope of this, let us say if I check this envelope, this is constant. Okay. Envelope means that the boundaries in which I can put the waveform. Okay. I think this envelope word you must have encountered when you were studying AM and FM. So I am not going into that concept of what envelope would be. That you can go back and read in that course. So you can see that PSK and FSK have a constant envelope. So what is the issue with constant envelope is that they are impervious to amplitude non-linearities. Basically, they are. So this word is from the textbook itself. Impervious means that they are not affected by. इन्हें कोई फर्क नहीं पड़ता. If you talk in Hindi, that is the meaning. So they are impervious to amplitude non-linearities. मीन्स एम्पलीट्यूड बढ़ जाए कि घट जाए उससे आपकी डिटेक्शन परफॉर्मेंस पे इफेक्ट नहीं आएगा। अल्टीमेटली जो आप डिटेक्ट करेंगे, आप फ्रीक्वेंसी का चेंज डिटेक्ट करेंगे एफएसके में और फेज का चेंज डिटेक्ट करेंगे पीएसके में। एम्पलीट्यूड कुछ भी बदल जाए, ये ऊपर हो जाए कम हो जाए, उससे आपको डिटेक्शन में प्रॉब्लम नहीं आएगी। दैट्स व्हाई द टू वेव फॉर्म्स एट लीस्ट, दैट इज बीपीएसके और एमएडीपीएसके, आई वुड से एमएडीपीएसके is widely studied and used. Okay, so that is one of the reasons. If you talk to an engineer who is working in the industry, he can give you at least 20 possible reasons. Okay, because when you talk in terms of all the hardware circuitry, all the issues faced, then you will find that the choice of a particular modulation scheme may not be as straightforward as we have stated. That just because amplitude change नहीं होता तो हम हमेशा PSK use करेंगे, ऐसा नहीं है. There are several other things because so an engineer who is really working in the industry will give you 10 different reasons. But as academicians or as people who are right now building base to work in the industry, this is sufficient. It means we know one thing which basically deteriorates our performance, that is the amplitude nonlinearities. Now what does the meaning of amplitude nonlinearity is that when it is going through the channel or it is going through the hardware, the amplitude of the waveform changes arbitrarily or in a non-linear fashion. Let us say x square times it happens. So if at all you have modulated the signal by changing the amplitudes, you will have a lot of trouble at the detector because your amplitude is now changing arbitrarily. Your detector will encounter a lot of errors. So that's why in a lot of cases PSK used. It says that PSK or FSK. I don't think we will be going through FSK, but PSK we will definitely be going through in the course, and QAM maybe. Okay. So that would suffice for this course, but you require another course on digital communication for studying other modulation schemes deeply. But at this level, it is fine, I think. Okay. So I think we have introduced this coherent and non-coherent. One thing I think forgot to mention. Let me go back to the notes where I have written coherent and non-coherent. Let me write one thing. Where it is. Yeah. Yeah, so this is what we were writing in the last lecture. So coherent means that if you have the exact carrier waveform at the receiver, so वो वाला case coherent होगा. I think I have not mentioned it here that what really is coherent. So when you have that you have the exact carrier at the receiver, which can really be the same as what the transmitter is using, means with the same frequency and same phase, you will say that the communication is synchronous. And if at all that is not the case, if at all you are having trouble, it means at the receiver the frequency is somewhat deviated from what it is being used at the transmitter, or the phase of the waveform is also not exactly what is used at the transmitter, then you may discard that carrier and say that now I am in a asynchronous communication. I don't have the carrier, so what is the way to detect? So in both the cases, detection and decoding is studied. But right now, for the case of coherent and non-coherent, that is the word. Synchronous and asynchronous should not be used. Sorry, it is a mistake from my side. Synchronous generally means that timing of the waveforms is exactly known. Coherent and non-coherent is the word which specifies that the carrier with exact frequency and phase is available. So the two words are coherent and non-coherent. Synchronous and asynchronous means that the timings of the sampling times are exactly same at the transmitter and receiver. So mostly in those contexts, these two words are used. So coherent communication पे हमारा focus शुरू में रहेगा. So we will be studying coherent BPSK first. So let me just write it down. So first we will be studying BPSK and that too coherent. It means we will assume that whatever carrier waveform or whatever sinusoidal signal we are using with the transmitter is exactly available at the receiver with no error in the frequency and phase. So BPSK means that it is binary phase shift keying. Now why you know the meaning of this word phase shift keying? It means that phase will shift between the levels. So it means phase के कुछ possibilities होंगी and for the symbol time a particular phase is maintained and then for the next symbol time a different phase is maintained and this way it will shift. And this keying will be from the message sequence which is coming. Now what is this binary means? Binary means that there are only two possible values in which the phase will shift. So अगर दो ही possible shifts हैं तो आप कितनी bit information encode कर सकते हैं? 1 bit information encode. So you have only 1 bit of information goes. Okay. So for 1 we say that there is a waveform that is S1t, and for 0 there is a waveform that is say S2t. Okay, and where, okay, let me see, maybe that my board is not functioning well, where S1t is equal to root of twice of EB by T B cos of, I think I should write below, into cos of 2 pi FCT. And this will exist in S2t is what? See, we have only two possible phase shifts, so the amplitude of the waveform will remain the same. You will ask that why have we chosen this as the amplitude, so we will get to know this. Into cos of, suppose we choose another phase which is 2 pi FCT. So here phase was 0, here the phase is pi, suppose. Okay, and this leads to, so this is equal to minus of root of twice of EB by TB cos of 2 pi FCT. So phi of 1 you have chosen as 0, phi of 2 is chosen as pi. So you have two possible phases. So this is two possible phases, so phases of the carrier. That is what the concept behind BPSK is. Now the question is, why only these two? From 0 to 2 pi, why only 0 and pi? So this you will get to know that because of choosing them to be the farthest possible apart. See, if at all, what has happened is, if this signal is in the positive direction, then this has become in the negative or exactly opposite direction. Now what this will lead to is, this will decrease your detection error. ओके, ये आपके डिटेक्शन एरर को घटा देगा, और वही हमारा पर्पस है. आप ये भी कह सकते हैं कि आई विल बी चूजिंग टू आर्बिट्ररी फेजेस phi 1 and phi 2, and then you can solve an optimization problem which will minimize your probability of error. Okay, so but that is not the way we will motivate our BPSK. We will motivate through the intuition. Intuition means that, let us say if this is the circle on which my different phase points lie, this is the 0th point, and this is, let us say, is pi, and these are the possibilities I have. So obviously, if at all I am choosing this as the one, I will exactly choose the opposite one, because this would be the farthest point from it. Okay. So this is one of the possible intuition you can have for this. Okay, because any other point, let us say if I take this, so it will take this. If I take this, so this is this. Okay. If I take this, this is this. So you will find that the farthest possible point is this. That is pi. If I choose it to be, let us say I can do pi by 2 also, pi by 2, then I will choose next point as 3 pi by 2. Okay, so I have to choose 2 points which are opposite to each other. Now why not pi by 2 and 3 pi by 2? Reason being that the beauty is that this takes the waveform as the same. Cosine ही रहता है आपका waveform, sine में convert नहीं हो जाता है pi by 2 की वजह से, और साथ साथ में प्लस और माइनस का चेंज रहता है. तो ये जनरेट करना, इसको स्टडी करना, डिटेक्ट करना इज इजी. ओके, so I am not motivating it from the perspective of, you would say, minimizing an optimization problem. I am simply saying that intuitively you can take this, because there is no need for us to consider that. अभी उसको स्टडी करना उस एंगल से कोई जरूरी नहीं. हम इंट्यूशन is sufficient for us to understand this or to model this. And remember that where it is important, where t lie from 0 to tb. So obviously हम लोगों ने जब इसको मोटिवेट किया था पासबैंड सिस्टम को, तो हमने यहाँ कहा था ts और t, that is the symbol time. But BPS के केस में क्योंकि आप 1 bit information को ही एनकोड कर रहे हैं, so your symbol time and bit time is same. So tb instead of t, there will be tb. Now there is one very important thing. Okay, this is a star thing. This is mentioned in Simon Hakin, and I feel that this is a very good thing ये author has mentioned. Otherwise this leads to a confusion. Now what is the confusion? पहली बात तो confusion लेते हैं. इसमें confusion क्या है? I don't know how many have identified this. Now I am saying this is a cosine carrier. Okay, suppose एक cosine carrier हम draw करते हैं. or this is your cosine carrier. Okay, this is going, and as per the FC frequency. Okay, this is T. Now I am saying that I am considering only an interval of 0 to TB. Now if TB is arbitrary, suppose I am taking TB as this TB. So I am considering a waveform which doesn't have complete cycles. Okay, इसमें क्या हुआ कि आपका एक साइकिल तो पूरा हुआ, बट सेकंड साइकिल का हाफ ही रहा. ये इतना आना चाहिए था कम से कम, ताकि आपके पास एक पूरी साइकिल आ जाए. So this TB and FC need to be linked together to create odd or even number of cycles or full cycle in that interval. Okay. So otherwise, what will happen is that whatever you are transmitting at the detector, there would be a problem. Okay. If it doesn't contain full cycle, then maybe in the synchronization or in several other things, you will have a trouble. Okay. So to ensure that each transmitted bit contains an integral. Now we are not going to the depth of why only integral number of cycles. Okay, integral number of cycles equals of the carrier wave FC is chosen as n upon pp. Okay, for some integer fixed and c. Okay, so 1 upon TB would be mostly the frequency content of the baseband signal, and you will be multiplying it some number n, integer n, positive integer n, and that would be a very big number because you have to basically go away from the DC. So let us say what really it leads to. Let us check that whatever we have mentioned in the figure, whether this is right or not. So let us check it out that what really is happening. So if you start out at 0, that is cos of 2 pi fc at 0. So this is something. Let us say then we start at cos of 2 pi fc, and let us say, sorry, let me do it in a different manner. Let us replace fc as n upon tb, and then we should study that what will happen if you terminate the waveform at tb. So let us say this is cos of 2 pi n upon tb into t. Okay. Now consider t lying from 0 to tb. So at 0, let us say this is, it takes the value at t equal to 0, this takes a value which is 1. But at t equal to tb, the value is cos of 2 pi n. Okay, so it means that it has undergone a rotation which is a multiple of 2 pi. Okay, it means now it will contain full cycle. I don't know if you can understand this. I think it should be easy for you to understand. Means अगर आप इसको angle मान लीजिए, suppose this is the angle, okay, and this whole is an angle. So angle starts at 0 and angle terminates as 2 pi n. So it means that it will have फुल साइकिल्स. 2 पाई का एक साइकिल होगा और n टाइम्स 2 पाई पे टर्मिनेट होता है एंगल 0 से स्टार्ट करके. तो इसका मतलब ये है कि जो टर्मिनेटिंग वैल्यू है दैट विल बी द वैल्यू एट व्हिच देयर वुड बी अ साइकिल व्हिच विल टर्मिनेट. ओके, दैट इज सिमिलर. So this logic works fine, that if you choose fc as n upon tb, so in the interval 0 to tb you will have always integral number of cycles. इसमें जैसे n cycles होंगे because it terminates in n into 2 pi. So, see, there can be several ways to understand this. I have just given you one of the ways to do it. If this is not working with you, then you can basically design your own method. Means हमें integral number of cycles चाहिए. तो आप समझ सकते हैं जब fc को n by tb रखेंगे और t की वैल्यू को एनालाइज करेंगे 0 से tb के बीच में, तो you will get integral number of cycles. This is one of the way to understand this. Okay. Now one thing. What is S1t and S2t? अब आपने देखा होगा S1t is root of 2 EB by TB cos of 2 pi FCT, and this is minus of, let me write it down so that it is clear. So S1t is what? that is root of twice of EB by TB. Okay, first of all, let us find the energies. Then I think things would be clear. Then we will go to the next point. So let us find what is the energy of S1T and S2T. So what is E of S1T? So this is nothing but 0 से TB उसका इंटरवल है. आप S1 square T dt कैलकुलेट करेंगे. What is it? 0 to TB. It is twice of EB by TB cos square 2 pi FC T dt. I think you must be remembering this from the signals and system days, but still I am doing it so that it is complete and it is in a single place. Now cos square theta you can write as cos 2 theta is what? 2 cos square theta minus 1. So 1 plus cos 2 times 2 pi FCT divided by 2. Okay. So I can write it down. Cos of 2 theta is 2 cos square theta minus 1. Okay, so it is 1 plus cos 2 theta by 2 dt. Let us check. This is twice of EB by TB. So it is 1 upon 2 into TB plus twice of EB by TB. So what I am doing, I am integrating cosine of 2 times 2 pi FCT over 0 to TB. Okay. What is this? This comes out to be TB. Okay, 2 cancels, TB division plus. Although I can leave it as a homework, but I am doing it. What this should be? Let us say if this comes out as a function of sine of, you can say 4 pi n upon TB into T upon 4 pi n upon TB, and you put the value as 0 to TB. So what it will be? Now sine of 4 pi n, because if you substitute TB, so TB and TB cancels, sine of 4 pi n is 0 minus sine of 0 is 0. So this whole term is 0. Okay, so this is into 0. So we will get the answer to be EP. So now you will understand that why did we use the scaling factor of root of twice of EB by TB. So this way we have ensured that the energy of the waveform remains as TB, and so E of S2T will also be equal to E of S1T because they both differ with a minus sign only, which is equal to EP. This should be now clear that why did we use this scaling factor? Root of twice of EB by TB. Now this scaling factor ensures that over the interval of 0 to TB, your waveform contains an energy of EB. Okay, so scaling factors are not arbitrary, they are done with a purpose, and if you understand the purpose, then there is no need to mug up the scaling factor. Okay, you can easily work it out yourself as well. Now what I was writing is, what I was writing was that if suppose S1T, now we are clear, we know that why the root of this twice of EB by TB comes, is given by cos of 2 pi FCT, and S2T is given as minus of root of twice of EB by TB cos of 2 pi FCT. There is a special term for such signals. They are called as antipodal basically. So a pair of sinusoidal waves, basically general term used for these is sinusoidal only, although it is cosine. Basically they are at quadrature. Cos means sine differed by a phase of pi by 2. So generally cos is sometimes mostly referred to as sinusoidal as well as a class of signals. So a pair of sinusoidal waves that differ only in a relative phase shift of 180 degrees are referred to as antipodal signals. Okay, so why? Because they are exactly opposite in phase. So I have just drawn, I think, I have rubbed the figure. So I think from there you can appreciate it. Now this is sometimes called as antipodal communication scheme as well. So BPSK and antipodal are exactly same, because antipodal means that if at all you have one phase, then exactly opposite one will be the antipodal. Okay, this is the name given to it. This is also used studied as a separate modulation scheme, but this is same as a BPSK. So BPSK is nothing but antipodal modulation scheme. Okay. Now, what can we say about S1T and S1T? Can we find out? Can we find out a suitable basis? So basically, the presentation in the textbook is in the reverse manner. First of all, they motivate BPSK कि दो possibilities होंगी फेस की, उसके बाद वो सिग्नल स्पेस के अंदर से उसका बेसिस फंक्शन फाइंड करते हैं. I think this strategy is good because first of all, let us get a feel of BPSK and then go into the signal space. Another possibility which you can say is complex somewhat is to first choose a signal space and then say what all possibilities we have. But that way at the UG level, you won't appreciate it. So in order for us to first appreciate what we are doing, we are studying what the scheme is, and then we are setting up a signal space over it. Why I am telling this is because you may ask that up to now we have been studying everything from the perspective of signal space. We are saying कि continuous time signals को हमने, we have find an analog vectors for them, and we are studying everything in the vector space or the Euclidean space. But why not the same for BPSK and QPSK? We will be doing the same thing, but first of all, we have identified what the modulation scheme does, and then we are working out the signal space things. Okay. So the question is, can we find out a suitable basis for this signal space? Signal space, you can say generated by BPSK. It means BPSK के दो पॉसिबल सिग्नल्स हैं. सो ये एक ना एक सिग्नल स्पेस को बिलोंग करेंगे, मतलब एक जनरेट करेंगे सिग्नल स्पेस. तो क्या हम बेसिस फंक्शंस बिलोंग फाइंड कर सकते हैं जिसको ये S1T and S2T, let us say, can we find a signal space in which S1T and S2T lie, and if at all there is a signal space, what will be the basis function for it? Okay. So let us this signal space to which the waveform generated by BPSK belong. So let me write the exact words. So can you find out a suitable basis for the signal space to which S1T and S2T belong? Okay. So yes, the answer is yes. Quite simple to see. Let us see how. So you can see that if we choose phi 1t. Now one thing, that this phi 1t, because this is the basis function, it needs to be unit energy. Okay. If we choose like this, twice of Tb into cos of 2 pi fct, where t lies from 0 to Tb. Okay. Then your S1t, then S1t can be written as root of Eb times phi 1t, and S2t can be written as minus of root of Eb times phi 1t. So what we can say that it requires only a single basis function. Okay, so it's a one-dimensional space to which your S1t and S2t belong. Okay, now remember that what is the energy of phi 1t? Because we have said that it is a basis function, so you can write 0 to Tb cos square of 2 pi fct, and we have seen that the answer to this would be Tb by 2. Here I think we have seen the remaining terms would be 0 and only Tb by 2 remains. So if I put it is twice of Tb into Tb by 2, which is equal to 1. So we have checked that phi 1t has unit energy. Okay. Now if I corresponding vectors corresponding to S1t, what will be the vectors? Vectors corresponding to S1t and S2t, what those will be? You can clearly see from this, since it is a one-dimensional space, so S of 1 1 would be root of Eb and S of 2, 1. Why? Because S2 represents the signal, that is this 2. This one represents this one, where this one represents the value for the corresponding basis function. So आपके यहाँ पे सिर्फ एक ही basis function है, otherwise यहाँ पे क्या होता है S12, S13, S14, यहाँ पे क्या होता है S22, S23, S24. So this is equal to minus of root of. So there are two things. So if at all in the signal space I say that this is the axis which is for phi 1 t. So there is a point which is root of EB here, then there is a 0 in between, and then there is a point minus of root of. So this is basically the signal space diagram for BPSK. We can just see in the textbook as well, so that if you are directly studying from the textbook, you can appreciate things better. Okay. So this is your BPSK. This is what is the case. So this phi 1 t is the axis. So you should not think that the x-axis is. No, we are drawing the axis in the signal space. So this axis represents a function which is phi 1 t. This is not your x, y, and z axis of the Euclidean space which you are generally familiar with. So here we have 2 points, that is root of EB. This is message point 1. This is message point 2. It means 1 corresponds to root of EB, 0 corresponds to minus root of EB, and this is 0 is in between. Right now we have not told anything, we have not discussed what this decision boundary is, but this is the constellation diagram, you can say. Okay. So what we can say right now, we can say that a coherent BPSK system. Now, why we are using the coherence, we will see that in the receiver design, we will be using this phi 1 t. Means we will assume that this phi 1 t is exactly known to us, correctly known to us. A coherent BPSK system is characterized a signal space is characterized by a signal space that is one-dimensional. This you can clearly see because the number of basis functions is 1, that is n equal to 1, and m is equal to 2. We have two possibilities, okay, because our system contains only two signals right here. Okay. So one important thing to check is if you are really very much into the vector algebra we have studied, so you can check that S11 is indeed equal to. So you project. So if you project your S1t onto your phi 1t. So this is the way to project in the signal space. We have removed the star because everything is real. So we will find that this is root of EB. And similarly, S of 21 is given by the projection of S2t onto phi 1t, which is nothing but minus root of. This you can work out. So this is just a. Okay, you can do it. This is quite simple. Now, one thing from the textbook, what we can see is what is the sort of what is really S1t and S2t. So this would be the case. So आप देखेंगे इसके अंदर कितना cycle है? इसके अंदर you have 2 cycles. So you have 2 full cycles. So if you say this is 0, then this is pi by 2, this is pi, this is 3 pi, this is 2 pi. So here this is one cycle, and then another cycle starts and it terminates fully at the TV point. Same is happening over here. Why? Because NC is chosen to be 2 for drawing this graph. Okay, so you can read it. This is figure 6.3 from the textbook. I think as I have told in the last 2 lectures that I am now strictly following Haken's book because towards the end of the course we do not have that much time to interleave concepts from different textbooks because that increases the required number of lectures by at least 3 to 4. Why? Because if at all BPSK I cover from one textbook and I need to highlight a few different things from another textbook, I require one more lecture. So if for one modulation scheme I require one extra lecture, then for 3 modulation schemes I require 3 extra lectures, and we don't have that much of time right now. Because of the pandemic, we already have 1 lecture less in a week. But anyways, during these tough times, if we have done at least 80 to 85% of the required thing, then we should be happy. Okay, so this is the way you will see the waveform at the receiver or at the transmitter as well. But for the study purpose, this is what is happening. Okay. स्टडी पर्पस मीन्स अगर इसकी हम डिटेक्टर डिजाइन वगैरह करेंगे तो हम थोड़ा बहुत सिग्नल स्पेस के कॉन्सेप्ट्स के अराउंड करेंगे. ओके, दैट इजीज अप आवर टास्क. Now we will do the generation and detection. That is important. How do you generate and how do you detect? So generation and detection of So I am again mentioning this word coherent so that to basically, if you listen it several times, then you will remember it. Okay. So let us see it. So instead of drawing, let us see what is happening. Okay. So figure 6.3. Let us see this. So if you can see this figure A, what we would be doing. So we are saying, let me first write it here. So what we are saying is, when we are saying that S1t is nothing but root or twice of EB by TB cos of 2 pi FCT. So what we are saying is that this one, which is I am now representing by SVT S1t. So this one exists from 0 to TB. Okay, 0 to TB, this one exists. Hence, from 0 to TB, this waveform exists. Same is happening with 0. So I am saying from, let us say 0 to TB, this 0 exists, and this is represented by S2T, which is minus of root of twice of EB by TB into cos of 2 pi FCT. Now, what is really this? This is NRZ waveform. Okay. So one thing we can do is that we can represent 0 by minus 1 as well. Okay, for the case of BPSK, we can just, you can say, smoothen it out. Okay. So one way to do it is that if I say that 0 is represented by a level of minus 1. Why? Because that way I can simply multiply my NRZ waveform with the K level. So one way, that is what it is. So can I do this? 1 0 1 1 0 0. Suppose I represent it by this, which is 1, then it is 0, then it is again 1 for 2 points, consecutive points, that is this is TP, and then this is 2 points as 0. Now if I multiply it with my root of twice of TP cos of 2 pi FCT, so what I will get is, and this is suppose level is root of EB, and this level is minus of root of EB. That is, I represent 1 as this 0 to TP, and I represent 0 as 0 to TP minus root of EB. Then by a simply product modulator, I am multiplying both of them, you will land up with the BPSK signal. Why? Because one will be represented by root of EB, that is under root of twice of EB by TB cos 2 pi FCT, and minus or 0 will be represented by minus of root of twice of EB by TB cos of 2 pi FCT. So for this, what you require, that there is a bit sequence 1010, so you have to encode it with the help of a polar NRZ waveform. So 10110011, you send it to a polar non-return to 0. I think we have done all of this. What is a polar NRZ? What is a polar, polar RZ? We have done all of this. So you can see this polar non-return to 0 level encoder will encode 1 with root of EB and will encode 0 with minus of root of EB. Now simply take a product modulator and you will have the BPSK signal. Now what will you do at the receiver? Now at the receiver, we know that the strategy is to correlate. Now for correlation, you will require the exact 510 which is used over here. And hence we have been stressing that we are under the ambit of coherent BPSK. That is, we assume that 510 is available or somehow we have exactly recovered it. मतलब जो भी रास्ते में problems आई इनको हमने correct करके इसको recover कर लिया. So the standard way to do the detection is just correlated with 510. So in order to correlate, we will multiply and integrate from 0 to t. Then you will get the decision statistic, that is x1 आएगा क्योंकि आपने प्रोजेक्ट किया xt को 510 पे. क्योंकि आपका सिग्नल स्पेस वन डायमेंशनल है, तो यू विल गेट वन पॉइंट. नाउ विद द हेल्प ऑफ दिस वन पॉइंट यू हैव टू डिसाइड, अब ये वन पॉइंट कहाँ लाई करेगा. दिस वन पॉइंट वुड लाई एनीवेयर हियर ऑन दिस एक्सिस, बिकॉज आपने अब रिसीव सिग्नल को उस पर प्रोजेक्ट कर दिया. प्रोजेक्ट करने के बाद वुड लाई somewhere on this axis. Now the strategy is that if it is greater than 0 then it is 1, if it is less than 0 then it is 0. Now this comes up from the detection theory which we have studied. Okay, means minimum distance decoder. So अगर आप minimum distance decoder निकालेंगे इसका, I would write that, go through. Basically why I am not drawing it is just to save time, otherwise I have to have drawn it here. But I am mentioning the figure so that you can just go in the textbook and see. So go through figure 6.5 in the textbook as written. So now अगर आप अब आपका ठीक है, आपने ये ट्रांसमिट किया था, this was 5 okay, and this was, let us say, root of EP minus this is plus root of EP. Okay, this is some 0.0. So your x lies somewhere on this, because what is happening is that whatever you receive, x of t you receive, it lies anywhere in the whole signal space. Okay, and we are concerned only with this one dimensional signal space which is represented 5 unity. So what you will do, this xt you will project on x 5 unity, so you get some point. Let us say this is what you get, some x. So what did you find this distance? राइट नाउ अब आप जीरो हटा दीजिए, मान लीजिए जीरो नहीं है रूल में. सो व्हाट यू डू इज दैट यू फाइंड दिस डिस्टेंस एंड यू फाइंड दिस डिस्टेंस. Whichever gives you the minimum value, you will decide its favor. Now you can say one thing, that if at all I assume there is a point 0 and there is a point, suppose EB and 1 is, I know if at all my x lies towards the right of 0, it will be always near to root of EB. And if my x lies away from 0 towards the left, it will be always nearer to minus of root of EB. So this minimum distance decoder then simply reduces to comparison of x with 0. Okay, I will write the minimum distance decoder. Since this decoder reduces to comparison of x with 0. I will write it down. Here you can see any point away from 0, is always nearer to root of EB than this to minus root of EB. And we will say vice versa. Okay, means the same happens for points, or the points which are towards the left of 0. So because of this minimum distance decoder then simply reduces to comparison of x with 0. Okay, so choose 1 if x is 1 is greater than 0, choose 0 if x1 is less than 0. This threshold is 0. Now this threshold is 0, why? Because you can say that if you start working out, let me go back to one of my notes where we found out what will be the lambda threshold. Okay, so if you can substitute the values in lambda threshold as well, you will get 0. Let me do it for you. Okay, let me just write down what was the optimum threshold value was, so that you can appreciate the same thing right now here itself. Just give me some time because I didn't write it in the notes that time, but right now only I am feeding that we should do that. Yes, okay, I found it out. So lambda opt we said was refer to notes. Okay, Okay, there were 2 notes of 2 to 3 lectures before. So lambda opt was n naught by 480b log of p naught by p naught. So we said that if p naught and p1 are equal, if p naught and p1 are, let us say, equal to some value a, or if at all they have to be equal and the sum has to be 1, then they have to be 1 by 2. So this a is always equal to 1 by 2. This has to be. Okay, if at all there are only 2 possibilities. So this leads to be 0. So anyways, आपने ML decoder जब डिजाइन किया तो you assume that the symbols are 1 and 0 are equiprobable. So in that case, your ML decoder comes out to be 0. But let us say there is a case, okay, that if at all they are not equiprobable, then you have to find the lambda opt as per this formula. Okay. Because this minimum distance decoder then is not optimal. Okay, means if you do it only on the basis of this minimum distance decoding, then this is not optimal. This implicitly assumes that message, the input message is equiprobable, because उसमें वो इन probabilities को रोल में नहीं लेता है. ठीक है? So this, I think you first need to study it, and then only you can appreciate it. But I am linking whatever we have done. Okay. So yes, I think we can go ahead and complete the error part, that is the final part for BPSK, and maybe after than that we can close. So let us start. To work out the error probabilities of BPSK. Okay. So what we can say? So from detection theory, so I would be skipping a lot of steps in between because we have properly covered it in the detection theory. So what we can say about f of x1, 0. What it would be? This would be a Gaussian random variable with this as the variance and everything. Okay, so this would be the, so this is all assuming equiprobable. Or this will be probable, you can say message values or 1 and zeros. Let me write 1 and zeros. So you will get that this is what is f of x1, x1 conditioned on 0 is this. अब ये मैं, I can go back and again write it down, but I assume that if you have a studied detection theory, studied means that I have covered it in the class, but if you have done it yourself as well, then you can directly find out that how do you get this. Okay, means आप मान लेते हैं कि 0 ट्रांसमिट हुआ है. अगर 0 ट्रांसमिट हुआ है तो मॉडल क्या आएगा? x1 is equal to s of 21 plus some w1. And this w1 will be a Gaussian random variable with mean of 0 and variance of n naught by 2. Okay, so this is distributed like normal 0 n naught by 2. So what it means that x1 minus s21 is equal to w1. Since w1 is distributed like this, so this is also distributed like this. That is one way you can say. Or you can say that this x1 now is a Gaussian distributed random variable with mean of S21 and variance of n naught by 2. So that is what you have done here. You just substituted in the formula of the, let us say what it is, mu and sigma square को कैसे लिखेंगे आप? I am just writing it for the sake of completion. 1 upon root of 2 pi sigma square e raised to power minus of x minus mu का whole square डिवाइड बाय ट्वाइस ऑफ सिग्मा स्क्वायर. सो अगर आप पुट करिए इसके अंदर, सो सिग्मा स्क्वायर क्या है, n नॉट बाय 2, तो 2 गेट्स कैंसिल्ड, सो यू विल हैव पाई ऑफ n नॉट and e raised to the minus of x minus of mu is s to 1 divided by n naught, because sigma square is n naught by 2, 2 gets cancelled. So that is the way you obtain it. Anyways, I have given it in a, I just explained it, and now it should be easy. Okay. Now what is P of 1, 0? Okay, now you know that 0 is transmitted. Now what is the probability that your detector will commit an error? Now वो error कब होगा? कब obvious है, जब आपने 0 भेजा है, तो अगर आपका receive point 0 से बड़ा हो जाएगा, मतलब इस point के right में आएगा, तो आपकी error हो जाएगी. So what do you do is you simply integrate this from 0 to infinity. It means what are the chances that even given that 0 is transmitted, your x1 lies away from 0, means 0 या 0 से आगे. तो उसका सिंपल मीनिंग है, इस कंडीशनल पीडीएफ को आप 0 से इंफिनिटी तक इंटीग्रेट कर दीजिए. तो दिस विल गिव यू द पॉसिबिलिटी ऑफ एरर वंस 0 is transmitted. So this is nothing but 1 by 2 ERFC root of EP by N naught. So we have done all of this, ERFC and EP by N naught. So I'm not explaining it further. I'm not doing this integration as well because I did it last time. Okay. Now what is P of 0, 1? So P of 0, 1 is, let us, I think I have not written it down, what is P of 0, 1, but this would come out to be same as P1, 0. Comes out to be. Or for the sake of completion, let me just mention it, that what is P of 0, 1, okay. That is not required because that will unnecessarily take up some time. You can do it yourself as well. उसके लिए कुछ नहीं है, आपका यहाँ पे क्या हो जाएगा, it will be having S11, okay. So you will be having x1 as distributed with a PDF of S11. Okay, what is f of x1? This will be like this. So this will be distributed, this will be equal to okay, and अब आप जानते हैं, if you have transmitted 1, then what is the possibility of you to choose 0 is you have to integrate from minus infinity to 0. F of x1, maximum condition dx1. Now you know, because of the symmetry of the Gaussian distribution and the way you do, it will be same as this. Okay, ये same आएगा. This is a homework to verify, comes out to be. This is a homework to verify. I'm deliberately leaving this as homework so that you have something to do on your own. Although you have a lot of things to do on your own, but this will be an interesting exercise. The reason for this is, so I'm giving you the reason, because signal space is symmetric, with respect to origin. Now what is P of E? That is the average probability of error. That comes out to be P of 0, that is P of 0 into P of 1, 0 plus P of 1 into P of 0, 1. So this is what you have a 0 transmitter. What is the probability that 0 appears in the transmitter, and the probability of making an error if you know that 0 is transmitted. This is the probability that 1 appears in the transmitter, and this is the probability that you commit an error given that 1 was transmitted. So this is, because this and this are same, so you can say this is nothing but P of 0 plus P of 1 into P of 1, 0, or you can say it is P of 0 plus P of 1 into P of 0. कुछ भी लिख सकते हैं. So this is always 1, this is 1, so this is equal to P of 1, 0 or P of 0, 1. Means कोई सी value which is same. Okay. So you can write now that, so bit rate, so bit error rate, so bit error rate for coherent BPSK for coherent BPSK, assuming equiprobable symbols. So this is important to mention because everything will change if they are not equiprobable. Because if they are not equiprobable, then the minimum distance decoder itself is not optimal. So you have to resort to the map route. Okay. Equiprobable symbols. First is, so P of E is equal to 1 upon 2. So this is a figure which you can remember as well. This is somewhat asked at different places. Even if you don't remember, you should somehow find out the way to decode it. If it is in your mind, so you can work it out. So that's there as well. So what you can conclude is that if EB increases, if this is important conclusion, if EB increases for fixed and not, means the variance of the noise is fixed, points will move apart in the signal space. Points move apart in the signal space that you can clearly see. Let me show you. So our signal space was this, that is root of EP, and this is minus of root of EP. Okay. Now अब आपने N naught सेम रखा और EB को बढ़ाते जाने तो what is this is increasing. This gap increases as EB increases. तो अगर N naught भी बढ़ रहा है तब तो कोई बेनिफिट नहीं है, बट अगर N naught उतना ही है, इतना मतलब ये है, इसका मतलब ये है कि अगर आपने ये ट्रांसमिट किया है तो जो नॉइस का पावर है वो सेम है, तो इसका मतलब वो जितना इसको डेविएट कर सकती है वो लिमिट उतना ही कर सकती है, बस जितना वो पहले कर रही थी. मींस N naught is fixed. So points will move apart in signal space, and this reduces P of E. So एक सिंपल तरीका है. अगर BPSK में आपको वो तो यहाँ से भी आप देख सकते हैं. So you can say that if my EB by N naught increases or EB by N naught decreases, what is the impact of P on P of E? Right now we can simply say that if EB by N naught increases, so EB by N naught को बढ़ने के दो तरीके हैं, या तो आप N naught को फिक्स रखिए EB को बढ़ाइए, या EB को फिक्स रखिए N naught को घटाइए. बट N naught भी आपके हाथ में नहीं है, तो what you can say is that I can increase my EB, assuming that my N naught remains fixed. It would be, because if it is a phenomena which is more or less in the circuit, then at a lot of times, or for most of EB, it will be fixed. Okay, for most of EB in the operational region, it would be fixed. So you increase EB. So once you increase EB, your EB by N naught basically increases, and once this increases, this falls. So ERFC function आप check कर सकते हैं, should be a falling function, should be a decreasing function of EB. Okay, so this reduces E. So एक simple आपका you have found out a simple way in which you can reduce PE in the BPSK system. So we are now done with BPSK except for its power spectra. Okay, that power spectra mostly you will get, most probably you will get it in the recorded lecture which I will put up. Most probably, it means otherwise it might happen that I put up only one lecture which is recorded and I do not discuss power spectra, although I want to. So today we are done with BPSK. On Friday we will start with QPSK, and I don't know up to what point we will finish it up, but whatever will be remaining, I will cover it up in another one or two recorded lectures. So on Friday we will be having our last lecture. Okay. So I would say that we are done for the day. So if at all you need to stop by to discuss something, you can. Otherwise, you can leave.